So today's lesson is going to be on the derivatives of exponential functions. So first what we're going to do is try to derive the formula for the derivative of an exponential function, a to the x. So we're going to use our definition from D1, f prime of x equals limit as h tends to 0, f at x plus h minus f of x all over h. We sub in our function, limit h tends to 0, ax plus h minus a to the x all over h. Now, based on our exponential rules, we can break up the a to the power of x plus h. We get a to the x times a to the h minus a to the x all over h. And we're going to actually factor this a to the x term out. So when I factor it out, I get a to the x times a to the h minus 1 all over h. Now I want you to pay attention. When we look at this term right here, this term has no h's in it. So this term is sort of like a constant when we're taking the limit as h tends to 0. So I can pull that out of the limit because it is a constant. So a to the x times limit as h tends to 0, f of x, a to the h minus 1 over h. So now we want to pay attention to this little expression right here. And if I look at f of x, which is a to the x, and if I compute f of 0, this gives me a to the 0, which is equal to 1. So this expression right here is literally f prime of 0, as if we were going to put that into our formula. So this would be f of x plus h, which our x would be 0, so we can come back and put 0 in for x, minus f of 0 all over h, which is exactly this expression that I'm replacing f prime of 0 with. So this limit becomes a to the power of x times f prime of 0, depending on whatever that value is. So this is representative of the derivative of the function x when you have a to the x. Now, when we look, this is kind of really important to pay attention to. It says that the rate of change, which is the derivative of any exponential function, is equal to or proportional to the function itself. So they say proportional because f prime of 0 is a constant and the derivative is equal to this constant times the original function. So the slope of the tangent line is proportional to the height of the function. Now when we look for different values, so we had limit h tends to 0, a to the h minus 1 over h, and we had a to the x on the outside. When we pay attention to this term for different values of a, so for example, when a is 2 or a is 3, we can numerically calculate this limit. And when we numerically calculate this limit, we see that this may be approaching a value like 1.09, and this may approach a value like 0.69. But we want to try to find the easiest value of this boxed expression, which is essentially f prime of 0. So if we can make this expression f prime of 0 equal to 1, that would be the best option for us. And we can notice here that this is the value produced when a is 2, and this is the value produced when a is 3. So if I can find some a value in between that produces that limit to be 1, that would be the easiest expression. So this literally is exactly what we just talked about on the last slide from the table, approximately. This was approximately 1.10 from the table. I wrote 1.09. I was slightly off. But here, this is the exact value of that expression correct to 6 decimal places. And if you actually look at this value, this actually works out to the ln of 2. And this part works out to the ln of 3. So therefore, if we're trying to find the derivative using this expression for any exponential function, if I were to take the derivative of 2 to the power of x, this is going to be proportional to this approximate numerical value we got off the table times the function itself. Or if I have 3 to the x, this is proportional to the value off the table times 3 to the x. Now these values we mentioned were kind of looking like ln of 2 and ln of 3, but you wouldn't have known that unless I just told it to you right now. So you want to pay attention that this ends up being the ln of the base, and the base is whatever your a value was here. Okay. Now, like we were saying, the simplest differentiation formula occurs if f prime of 0 was equal to 1, and if that were the case, then f prime of x would be just equal to a to the x, which makes the formula quite simple, but this is only true when we can find the value of f prime of 0 equaling 1. So what our goal is to try to find which function has the derivative at the point 0 to be equal to 1, and we do know that that value is between a is 2 and 3. So we're saying that there is some reasonableness to assume that there is going to be a value for this, and then this is where the definition of e comes in. So we define e to be the number so that when we end up taking this fancy limit, which represents f prime of 0 of our limit formula, this is exactly equal to 1, which is what we want. So what this is saying to us is if I want to do the derivative of e to the x, the derivative would be e to the x times f prime of 0, and in this case f prime of 0 is just 1, because that's how we choose to define that value. But in the other cases, when I had derivative of 2 to the power of x, this is proportional to not e to the x, 2 to the x. So this is proportional to 2 to the x times that value we got as a constant earlier, which was 0.69 approximately. But this is exactly going to be equal to ln of 2 times 2 to the power of x. So this, geometrically, this is quite powerful, the result we just obtained, because if we choose our function to be e to the x, this is really crazy because the slope of the tangent line to the curve at any given point is actually the y value at that given point. So if I want to do the derivative of e to the x, I know that the derivative is going to stay e to the x. So if I want the derivative at, say, 2, this is just e to the 2, which is like the y coordinate at that point on the original function. So that's quite powerful because no other function does that. Okay, this is the end of part 1.